Hi guys, it's me, Sir Ernest, and today we are going to illustrate how the normal modes of motion of n particles for a loaded string is illustrated, or how do they look like. Now, as I recall, okay, so the position of the n particle of the of a particle in the loaded string in the J mode is given by y. Okay, so this is the position along y because we assume that the particle is moving in the vertical direction and it oscillates as a function of time. N is the n particle and then J is the mode of oscillation, and this is equal to dj, which is the some maximum displacement for the J mode, times sine nj pi over n plus 1, where small n is the n particle and capital N is the total number of particles, times cosine of 2 square root of tau over md times sine j pi over 2 n plus 1 t plus v j. Okay, so from here we already know that this is the some amplitude term and this is your oscillating term, so this is your omega for that mode of oscillation J. Okay, now let's see, for example, for the sake of illustration, first let's illustrate two particles. So we have two particles, so that means n is equal to 0. So if we're going to draw it here, somewhere here, it looks like this. So if this is the ends of your string, so we have two particles. Okay, so this particle and this particle will oscillate in this direction only. Okay, so let's say initially, let's put in some initial values. So at time equal to 0, let's at time equal to 0, then we have, for example, j equal to 1, and then let's set, for illustration purposes, the maximum displacement for the whole system would be equal to 1, and lastly the phase constant is also 0. Okay, so let's compute for y. So y for the first particle in the first mode, okay, at time equal to 0. So in this case, essentially for all our calculations, this will be 0 and this is 0. So we're just looking for this term. Okay, so dj is equal to 1, then that's sine, this is sine times n equal to 1, j equal to 1 pi over 2 plus 1 will be 3. So that's sine pi over 3, which is equal to 0. Approximately equal to That's what? Square root of 3 over 2, no? Okay. Right? Or no? Anyway, this is approximately equal to 0.866. Again, this is n equal to 1. This is n equal to 1. And this is j equal to 1. First mode. For the second mode, this will be sine. This is 2 times 1 times pi over 3. And this is also equal to 0.86. If we're going to draw this, it would look something like this. So, okay, so let's say this is your equilibrium position, and this is your let's say this is your position of n equal to 1. By the way, this is also this is the position of n equal to 2. So this is your loaded string. A loaded string composed of 2 particles. So let's say this is the position of n equal to 1, and this is the position of n equal to 2. And let's say this is equal to 1. I hope you can see it in the video. And this is equal to negative 1. Okay. So that means for time equal to 0 at the first mode, the first particle will be here. So that's 8.66, and the second particle will be here. So if we're going to connect it, it would look like this. This is your first mode. Okay. So now let's look at let's talk about this later. Okay. So let's go to the, let's say at j, so same time dj and phi, but this time j equal to 2. So this is y1, so the first particle at the second mode. So this is equal to sine 2, this should be 1, n equal to 1. Okay, so this is equal to 1, then j equal to 2, then pi over 3. Okay, so that's 2 pi over 3. Sine 2 pi over 3 is also approximately equal to 0.866. And what happens if we consider the second particle n equal to 1? Remember, this is n equal to 1. N equal to 2. This is n equal to 2. This is 0. Okay, so y of the second particle on the second mode will be equal to sine 2 times 2 times pi over 3. So that's 4 pi over 3, and this is approximately equal to negative 0.866. If we're going to draw that, it would look something like this. and then this is 0. Okay, and then let's consider 1 here, and this is negative 1. Okay, and then this is going to be projected like this one. Okay, and then n equal to 1, and then n equal to 2. Okay, so our first particle n equal to 1 would be in the same position as this, but the second particle n equal to 2 would be here. It will look like this. Okay, now comparing the two, okay, so what happens here is this. This is particle 1 and this is particle 2. Okay, at any given point in time, the particle 1 and particle 2 will be with the same vertical displacement. So as this oscillates, it would look, as this progresses, it will move like this. Okay, so you will notice that this is actually a symmetrical mode. Okay, so this will move like this. On the other hand, n equal to 1 is here for the second mode, n equal to 2 is in this mode. So what happens here is that the oscillation of these two particles would be like this. Okay, so as you know, as you guess, or as you know, or as you identify, this is an asymmetrical mode. Okay, so remember your coupled oscillator of two particles, it's the same thing. Okay, now what happens now, as I mentioned before, that J only has value equal to 1, 2, up to n. And why is that? Okay, why is the limiting value of J would be the number of particles? Because we already assumed before that the number of modes for a coupled oscillator will depend on the degrees of freedom, and usually that is dictated by the number of particles involved in the coupled oscillator. Now let's see what happens if we have J equal to 3. Okay, so this is y1 3, so this becomes sine 1 times 3 over pi divided by 3. So this is sine pi, which is equal to 0 exactly. And similarly, for the second particle, this is sine 2 times 3 times pi over 3. So this is sine 2 pi, and this is equal to 0. So if we're going to draw that like this one, so this is 0. So we know that this particle n equal to 1 and this particle n equal to 2 will just be located here. Okay, and it's always here because this is always 0 for J equals to 3. Okay, so sometimes, or usually, we call this the null mode, and that's why the limit for J is always equal to n. Now let's see what happens if, for example, we have J equal to 4. Okay, for J equal to 4, y1 4 would be equal to sine 4, sorry, this should be 1, n equal to 1 should be n equal to 1 4 pi over 3, which is approximately equal to negative 0.866. ny24, which is sine 2 4 pi over 3, and this is equal to 0.866. So if we're going to notice, we can draw it like this. Okay, so this is 0. This is, let's align it here. So this is plus 1 and this is minus 1. And this is n equal to 1 equal to 2. Now for n equal to 1, that's negative 8.66, so this one. And then for n equal to 2, that's 8.66. So the position of your particles will be like this. As you will notice that j equal to 4 is just the same as j equal to 2, but in opposite direction. Okay, so this is actually a part of this one, as these two particles go this way. Okay, so as a summary, as you can see, only j equal to 1 and 2 are unique or are distinct modes, because j equal to 3 is a null mode. If you increase further the j, like for example j equal to 4, that will be the same as, or a duplicate of, one of the first earlier modes. In this case, it's a duplicate of j equal to 2, or the second mode, with the change of sign. So this illustrates that indeed there are only capital N distinct modes, and that increasing j beyond this n will just duplicate the modes for the smaller n. Okay, so what I want you to do is to try this as well, but this time I want you to do n equal to 3 and n equal to 4, and see what it looks like and how does their first and second modes compare to the first and second mode for n equal to 2. Sorry, this should be n equal to 2. Okay, so that's all for now. Thank you for watching, and I'll see you guys in the next video. Bye bye.